Hello everyone, welcome back. Uh, in the last module, as I told you, I will discuss about DC circuits. Then from the last video, I have started magnetic circuits. That is the second module, and we discussed some important things, some terminologies and various. It was a revision type of class in which all the basics were discussed about magnetic circuits. Uh, and different terminologies also we have discussed. So from in this video, I'll discuss about the terminologies and certain other topics which are related to the second module. So let us begin. So I hope you remember in the previous video I discussed about electromagnetic relationships. Their reluctance and permeance were discussed. Reluctance, it is a property just like resistance, and permeance, it is a property just like conductivity or conductance. Now I'll discuss about magnetic field strength. So what is magnetic field strength? See, it is denoted by H. Okay, it is denoted by capital H. It is given by the force experienced by unit north pole placed at that point. The force experienced by any north pole when placed near a in the magnetic field. That force is termed as magnetic field strength. The strength with which the force which the north pole will face when it is placed near the magnetic field, that is known as the magnetic field strength. It is denoted by capital H, as I told you. Now if phi is the flux in Weber, flux is denoted by phi. So if phi is the flux in Weber, F is the force in Newton, H is the field strength in Newton per Weber. So what is H? It is the force per flux. So it is H is equal to what? F by phi, Newton by Weber. H is also given by H is equal to B by mu naught mu R. B is the flux density and it is the permeability. Now I will tell you what is permeability. Okay, so H is P divided by mu naught mu R. Mu naught is the permeability with of a vacuum, we can say, and it is a relative permeability of some material with respect to some other material or with respect to air. Okay, so next topic, next topic is permeability. The magnetic conductivity of iron as compared to that of air is called permeability. Magnetic conductivity, the how much conductive is the magnetic field, the magnetic conductivity of iron as compared to that of air is called permeability. Absolute permeability is written as mu of a medium, and mu is given by B by H. B by H will give you mu, right? So mu is given by B by H. Now if it is only mu, it is called absolute permeability of any particular medium. So it is mu is equal to B by H, if where B is the flux density and H is the magnetic field strength. Okay, and mu is also given by the equation mu is written as mu naught mu R. So here see, this mu naught mu R, it is written as mu, that is the absolute permeability. Mu is also given by equation mu is equal to mu naught mu R. So here this mu is equal to mu naught mu R. If I replace here, we'll get the previous equation, where mu naught is 4 pi into 10 to the power minus 7 H per m. 4 pi into 10, this value of mu naught is equal to 4 pi into 10 to the power minus 7 H per m, and mu R is relative permeability. The relative permeability mu R of a medium is given by B by mu naught. These are all certain formulas which you may require for solving problems. These values will be given in the problem. Okay, no need to worry. Only the thing which is have to be calculated by using the given values. So in given values, these values will be there. What is B? B is the flux density in medium under consideration, and B naught is the flux density in vacuum. So mu r is equal to 1 for air. Relative permeability for air is 1. Okay, so this is if it is not also given in problem, then if it is mentioned that the medium is air, then it is understood that mu r, value of mu r will be equal to 1. So these are the things related to permeability. Now analysis of magnetic circuit. Magnetic circuit is defined as a closed path. Now what was electric circuit? It was a closed path in which electricity used to flow, right? Same way magnetic circuit will come. A magnetic circuit is defined as closed path traced by the magnetic lines of forces. The closed path which is traced by the magnetic lines of force are known as magnetic circuits. Okay. Now magnetic circuits can be divided into three: simple magnetic circuit, composite magnetic circuit, and parallel magnetic circuit. One by one I will discuss about all these three. Simple magnetic circuit. It consists of a closed iron ring. The ring it will consist of a single material, so it is mainly made up of iron. It consists of a closed iron ring. See, a ring is there wound with magnetizing coil as shown in figure. These are nothing but coil. So a ring, an iron ring coiled, wound with a coil. The magnetic, this is the case of simple magnetic field where only a single iron rod or iron ring is there upon which coils is wound. The magnetic flux is produced by the coil, right? When the current flows in the coil, magnetic flux will be produced. Thus, the coil acts as a source of MMF. So, the coil, it will act as source of MMF because here some source will be connected, and it will, because of the flow of current only, the magnetic flux will be created, right? So, it is known as the source of MMF in this case. And the reluctance for establishment of magnetic flux is offered by the ring. So, as current flows in the circuit, resistance is offered by the conductor. Here the reluctance will be offered by the iron. The toroidal ring of n number turns, suppose it is having n number of turns. I is the current flowing, phi is the flux in the iron ring, A is the cross section, and L the length of magnetic path, and these are the values. Okay, then these are the formulas which we get. The magnetic flux density is B phi by A. We all know, as I told in the previous lecture, B is equal to phi by A. Also B is equal to mu naught mu r. So H is equal to this, but H is equal to this as well. Go to the previous slides, you will come to know. H is equal to Ni by L. So if after replacing here, we'll get this formula. So phi from here is Ni by L by mu naught mu r A. This is nothing but this is the reluctance. Okay, this is nothing but this is the reluctance. So this is simple magnetic circuit. Okay, this is in case of simple magnetic circuit where only one type of iron ring was there. A ring was there which was made up of only one type of material, that is iron, and on this material rings are coils are wound, and coils are wound. So these are the formulas associated. B is equal to phi by A, B is equal to mu naught mu r H, and from here we can write H is equal to Ni by L. Then after replacing, we'll get this, and we'll get this. Just go through their formulas, you will come to know how to solve it. So Ni by L by A, this denominator is nothing but it is the reluctance of the circuit. Okay, reluctance offered by the circuit. Now in case of closed magnetic circuit. Now this is a magnetic circuit. This is a closed ring. See, this is a closed ring. But difference is what, in the previous case, this whole ring is composed of iron, and the whole area of cross section is same. For the overall iron ring, cross sectional area is same. But in this case, in case of composite magnetic circuit, see, this is the ring. For this part, see, area of cross section is different. For this part, area of cross section is different, and for this part, area of cross section is different. Let this be A1, A2, and A3. Okay. Moreover, The materials can also be different. So what happens in composite magnetic circuit? Practically the magnetic circuits are formed by more than one material. Okay, it is formed by more than one material with different permeability. Of course, when material changes, permeability will also change. Such material can give various length and cross-sectional area. This circuit is called composite circuit. Okay, this type of circuit is known as composite circuit. When those materials are connected one after the other to form a magnetic circuit, it is called to be a series magnetic circuit. And these are connected one after the other, right? This type of material connection is known as series magnetic circuit because this portion material, this material and this material, they are connected end to end, right? They are connected end to end. So this is, we can say, a series connection. Okay, so when those materials are connected one after the other to form a magnetic circuit, it is called a series magnetic circuit. Now what happens about the formula? See, if n number of turns in the coil, total mmf will be Ni, reluctance will be S. Now total reluctance will be sum of individual reluctances, like just like resistance. Since it is series, so the reluctances will be added up. S is equal to S1, S2, S3. So total flux is total mmf by total reluctance, total mmf by total reluctance. So it will be uh, now if we are supposed to find out total mmf, then it will be total flux into total reluctance. So total flux is phi and reluctance is sum of this. So this we get phi is equal to S1 plus S2, phi into S1 plus S2 plus S3. Now reluctance is what? L by mu naught mu r A, where A was a cross sectional area, right? Here three cross sectional areas are there, so 3 times it will come, and length is also different. So L1 for the first cross section, see the diagram, you will come to know L1, then A1 is the area of first material, L2 length, and A2 second material, L3 is the length and cross sectional area, A3 is for the third material. So like this, if I give, the total mmf is obtained like this. So we know that flux is equal to B by A, so total mmf is this. So B is equal to mu H, and we get total mmf as this. So from this derivation for a series circuit, the magnetic flux through all materials is same. Okay, magnetic flux through all materials will be same, but the reluctances are different. Okay, like in series, current is same. In series connection, current is always same. So here magnetic flux will be same, right? Then the equivalent reluctance is the sum of individual material reluctance, say S1, S2. S was equal to S1 plus S2 plus S3, that is what it is saying. The total mmf required is sum of mmfs of individual material. In series, total mmf or total in series, if we talk about electric circuit, V was equal to what? I1 R1 or IR1 plus IR2 plus IR3, like that, right? So here also mmf is equal to H1 L1, H2 L2, H3 L3. Okay. So total mmf is a sum of mmfs of individual material. Individual material, sum of individual material mmf experienced by the individual material. The total mmf will be sum of all those individual material. Now parallel magnetic circuit. See, this was a series magnetic circuit. This is a series magnetic circuit, right? Because magnetic materials are connected end to end. So this is a series magnetic circuit. Now we'll talk about parallel magnetic circuit, where this is one path, this is one path, this is one path, this is one path. So a magnetic circuit is said to be parallel connected if it has more than one cross path for flux. This is one cross path, this is one cross path. So if more than one cross path is there, then the circuit will be known as parallel circuit. At point B, flux have two paths. See, flux, some flux is generated here, but after coming here, this is one path and this is another path. So flux phi 2 passes through path BE and flux phi 3 passes through BCFE. BCFE. See, right? There, here it is. Here phi 1 was there, and after coming here it gets divided into two, phi 2 and phi 3. So we say that this type of circuit is known as parallel circuit. Now phi is 1 is equal to phi 1 plus phi 2, because current, just like current I was equal to I1 plus I2, so here also phi will be equal to phi 1 plus phi 2. S1 reluctance, S2 and S3 are 3 reluctance, right? So total mmf path this, total mmf path this will be, total mmf is Ni, it will be phi 1 into S1, phi 2 into S2, the mmf. Okay, after solving this we'll get S1 is equal to this, S2 is equal to this, S1 will be same, S2 will be same, S3 will be same. Okay, so this is how the parallel magnetic circuit works. Okay, so I hope you understood about the different types of magnetic circuits. For your course, simple and composite magnetic circuits are required. Okay, so for your course only this thing was required. Now magnetic leakage flux. What is leakage flux? See, this is a ring. Okay, iron ring, but there is a gap. Okay, there is a gap. So the flux that flows an undesired path is called a leakage flux. So due to this gap, this is a useful flux. But see here, this is the air gap, and here iron core is iron. On this iron core, conductors are wound and it has become a coil. So this is a coil. This is the leakage flux. Now I will come to leakage flux. This is the useful flux, air gap, and this is the iron. Okay. The flux that flows an undesired path. This is the flux will be created here, right? But some flux will be created here also. See, that is the leakage flux. The flux that flows and follows an undesired path. That is not the desired path. Our desired path is this. It should flow in this coil, but there will be some leakage. To utilize the magnetic flux established by the magnetic material, we provide an air gap. The gap in the flux in the air gap is called the useful flux. The flux which does not pass through the air gap cannot be utilized, and hence it is considered as leakage flux. The flux which cannot be determined by compass or which cannot be utilized is called the leakage flux. Through this leakage flux, though this leakage flux does not affect the efficiency of the electrical machines, it does increase the weight and cost, and hence it is undesirable. Okay, it cannot be totally avoided. So this is a leakage flux which follows the undesirable path. Now this is very important, comparison of electrical and magnetic circuit. All throughout these videos I talked about, like see, in electric circuit this happens, like in magnetic circuit this happens, this is reluctance for magnetic circuit, then resistance for electric circuit. So we see that there is a similarity between electric circuit and magnetic circuit. So it is very important to study the comparison of electric and magnetic circuit. So here is a topic where we discuss about the similarity. So first, magnetic circuit. The path traced by magnetic flux is defined as magnetic circuit. Okay, that is a closed path that is traced by the magnetic flux. Okay, that is the magnetic circuit. Path traced by the current is called the electric circuit. Path traced by the electric current, when the path is closed, the path traced by the electric current is called the electric circuit. MMF is the driving force. As I told you, MMF is it is a driving force which drives the flux through the closed path. And EMF is the driving force in an electric circuit. In an electric circuit, EMF was the driving force, whereas in magnetic circuit, MMF is the driving force. There will be the presence of flux. Okay, in magnetic circuit, flux is there. There will be presence of current I. So in electric circuit, current will be there and not flux. In magnetic circuit, flux will be there, but in electric circuit current will be there. The magnetic lines will decide the flux. Field lines, they decide the flux, but in electric circuit the flow of electron decide the current, right? The flow of electron decides the current. Opposing force of flux is reluctance. The force which was offered by the magnetic material to the flux, that is known as the reluctance. Opposing force for current is resistance, and the opposing force provided by the conductor to the flow of current is known as the resistance. It is given by S is equal to L by mu naught mu r A. It is given as R rho L. See the similarity. See the similarity. Rho L by A. It is also L by A, but in place of rho, another thing comes. Right? See the similarity. It is very similar. Flux phi is equal to mmf by reluctance. Phi is given by mmf by reluctance, and I is given by EMF by resistance. The force V by here, it is V by R I. Phi is equal to the force mmf by reluctance. So mmf becomes EMF in electrical circuit, reluctance becomes resistance in electrical circuit, and phi becomes the current in the electrical circuit. Reciprocal of reluctance is permeance. When we find out the reciprocal of reluctance, that will give us permeance, and when we find the reciprocal of resistance, it will give us conductance. Okay, so these are the similarities of electrical and magnetic circuits. Okay, huge similarity, you can easily compare and find out. Now dissimilarities. So with similarities come certain dissimilarities. What are the dissimilarities? The flux will be just established in the circuit because of magnetomotive force, but it will not actually flow in the magnetic circuit. But the current flows in the magnetic circuit. Okay, magnetic flux is created, but magnetic flux does not actually flow. But in electric circuit, actually current is flowing. Actually electrons are flowing. Electrons are moving, right? But in magnetic circuit, nothing of such sort happens. Energy is required to create the flux and not to maintain it. When once the flux is created, energy is required just to create the flux and not to maintain it. But energy is required to create and maintain the current. But to maintain the flow of current, there the energy is required it is required for production as well as to maintain the flow. Energy is required. Okay, so this is dissimilarity between magnetic and electric circuit. Next comes magnetic lines of forces are closed. As I told you about the bar magnet, the lines of forces are closed. They flow from north pole to south pole externally and south to north internally. But in electric lines of flux is not closed. They start from positive charge and end on negative charge. Okay, it is not that it will flow internally also. It starts from positive and ends at negative. So this is another dissimilarity of magnetic and electric circuit. There is no continuous consumption of magnetic energy. There is continuous consumption of electrical energy. So in magnetic circuit, continuous consumption of magnetic energy is not there, but in electric circuit, continuous consumption of electric energy is there. Okay, so these are certain dissimilarities between the magnetic circuits and electric circuit, and also similarities between magnetic circuits and electric circuits. Now I'll go to another thing. Okay, these are the various issues, various terminologies related with the subject. Now I move to electromagnetic induction, next topic. So before for discussing electromagnetic induction, we'll require laws. So let us discuss. We have seen that magnetic effects of electric current we have studied. Then it was Michael Faraday who made attempt to get EMF from magnetic flux. This is called electromagnetic induction. Now what happens, I will told you. So it's Michael Faraday, he discovered this thing, this property of electromagnetic induction. So let us see, he formulated one law which is known as the Faraday's law. Now let us understand what is Faraday's law. Whenever the magnetic flux linkage linking a conductor changes, an EMF is always induced in it. So see, whenever, as I told you, whenever a current in conductor is given a certain, sorry, whenever a conductor is made to, some current is made to flow through the conductor, the magnetic flux is created, right? The magnetic flux created is, it is not instantly created to suppose 100 and again it becomes 0. It slowly increases from 0 to a certain value, right? The value of flux, it increases slowly from 0 to a certain value. So there is a change in flux, right? There is a change in value of magnetic flux. So whenever the magnetic flux linking with the conductor changes, so the flux linking with the conductor, if it is in the vicinity of the magnetic field and the conductor is experiences difference in magnetic flux, the intensity of magnetic flux is varying, then an EMF is induced in the conductor. Am I clear? Whenever a magnetic flux linking a conductor changes, then an EMF is induced in it. The magnitude of induced EMF is proportional to the rate of change of flux, and the rate with which the flux is changing, the EMF induced will be proportional to that rate of change of flux. This is Faraday's law. Okay. Whenever magnetic flux linking a conductor changes. So whenever flux which is linked with the conductor changes, whenever change in flux is there, an EMF is induced in it. Okay. And always an EMF is induced in it, and the magnitude of induced EMF is proportional to the rate of change of fluxes. So we say that E is proportional, E is equal to d phi dt. Proportional, if I say E is directly proportional to d phi dt, and if the proportionality is removed, then this constant n comes. So E is equal to induced EMF in V, n number of turns, and d phi dt is the rate of change of flux. So this is nothing but Faraday's law. Another law comes out from here, Lenz's law. Sorry for the spelling, it should have been Lenz's law, Lenz apostrophe s, okay, Lenz's law. This law states that any induced EMF will circulate a current in such a direction so as to oppose the cause producing it. The current is flowing in the conductor due to which a magnetic flux is created, right? Now due to the change in magnetic flux, the value of the magnetic flux, an EMF is induced in the conductor. Now there should be some direction, some polarity of the EMF, right? So the polarity of the EMF, the direction of the EMF will be such that it will oppose the cause producing it. Whatever is the cause of production of EMF, that EMF, the polarity will be such that it will oppose that direction. Okay, it is always oppose the cause inducing it. So what is the cause? The cause is the change in flux. So what is E? E is equal to, so we gave a minus sign because it is opposing, right? So E will be equal to minus n of d phi dt. Change in flux is resulting to E, so a negative comes because it is opposite to the change in flux. Okay, so this becomes Lenz's law. This was Faraday's law. Faraday said that the rate of change of the EMF induced will be proportional to rate of change of magnetic flux. What Lenz's law says, that the rate of the EMF induced, whatever is the induced EMF, that will be the polarity of the induced EMF will be such that the direction is opposite to the cause producing it. So it is E is equal to minus d phi dt. Okay. Now E is what induced EMF, and is number of turns, d phi dt is the rate of change of flux. Okay. So these are the two laws of electromagnetic induction associated with electromagnetic induction. So I will discuss the rest topics. There are many other things which has to be discussed in this module. I will go discuss everything one by one. So this was all for today. I'll discuss the things in the next video lecture. Okay. Thank you very much for watching.